streaming. I guess you can call this pre-spooling. And I'm gonna get my text terminal ready. Alright, there we go. Alright, so it is time to get started. The first thing we're going to do today is to go over the homework assignment, which was due in about 30 seconds ago. So we'll go ahead and get started with that. Even though I did not or may not have provided a main, which maybe not, in case someone said that I did, it's not really that necessary, because all we need to do is to set up a call, with some value as our argument, and then we can test it. There's really no need to store into a local variable in main, because we have the trace analyzer. Okay, so the trace analyzer does allow us to debug programs in a fairly convenient way, but it does require some proficiency of using LogicSim on the command line, and also to make use of the trace analyzer. So what we'll do is we're going to start with the definition of the Fibonacci program, and here is the label fib, and then we want to look at what the stack should look like at the entry point of the subroutine. So we got n, which is a parameter pushed on the stack, the return address, which is also pushed on the stack, and that's it. Okay, the stack pointer should be pointing to return address on the stack, because that was the last thing that the caller pushed on the stack. So we know this has to be what the stack should look like, because this is the agreement between the caller and the callee, and we are now looking at things from the perspective of the callee, the subroutine being called. Alright, so the next thing we need to do is to implement the ternary expression, and you probably find out that I really like to use ternary expressions because I find it to be quite useful. I know it is not as intuitive as a conditional statement, but you can do certain things with a ternary expression that you cannot do with not as easily, with a conditional statement. So that's why I personally prefer to use ternary expressions. So regardless, the first thing we need to do is to determine whether n is less than 2 or not. And n is unsigned, is an unsigned 8-bit integer. So to compare to 2, there's no really easy way to do it. You first have to get n into a register first. So we have talked about how to use labels. Okay, so we're going to define some labels here. So in this case, I'm just going to use fib underscore return address, and that is a label defined to be 0, which basically means it is representing the offset of where we can find the return address in this particular subroutine relative to where the stack pointer points to. So that part is really important. And then n is just 1 byte after that, so it's fib return address 1 plus. Now technically speaking, if I have other subroutines, even n can be a name that is used by other subroutines, so it's better to use fib underscore n. But since this is the only subroutine for this entire program, so I'm not too concerned about that. And I know that I'm missing the no-op and the JMP-I to go around the definition of fib, but we can deal with that later. We'll focus on just the subroutine at this point. So the first instruction is LDI-A. At this point I can use register A, B, or C. All three can be used for this purpose. I just like to use A first, and then if I cannot use A, then I move on to B, and then I move on to C. So what we do is we load it with fib return address, just like that. So it's an offset, and then we add the stack pointer to register A, so that register A becomes the address. Oops, I forgot. Okay, my bad. We want to access n, not the return address. So it should be n. So by the time we are done with the add instruction, we would have the address of parameter n in register A. So at this point, if I do a LDAA, I would have the value of the parameter in register A, which means I'm almost ready for the compare. But I cannot compare A with 2. This doesn't work because compare can only compare between two registers. So that means I have to put the constant that I want to compare to into another register. So I have LDI B2. So now I can actually do the compare. So when I do the compare, we kind of have to consider the two possibilities, because I could compare it as compare AB, or I can compare it as compare BA. Now, which one makes more sense? Well, we want to confirm or not confirm that n is less than 2. So it makes more sense to use compare AB. And then after this, we're going to use a JCI instruction. It is JCI and not JLI, and it is not JSI, because n is an unsigned 8-bit integer. So that is why we need to use JCI. Now, some of you may want to point out and say, but I used JSI or JLI and the program seemed to work. Well, it is going to work because the range of values that we can use to pass a parameter n can only go from 0 to some relatively small value, because otherwise we run out of the stack space, and it will also take a long time to finish the computation if we had enough space. But that does not mean JSI or JLI is correct. So in this class, even if the program works, okay, quote unquote, it works in some cases, but if the concept is wrong, I will still take points off, okay, because it is about understanding which one we should be using and not focusing on whether the program works for the limited test cases that we can feed into this program when it's running inside the toy processor. Okay, so now we have a JCI. If it is indeed less than, then we do not have recursion, and we'll just go ahead and return n. So I'm just going to label, make this label fib underscore return n. So that means, if I continue execution, then this is the recursive case. All right. So what I do here is I am setting up the control structure. And if I do want to return n, there's really nothing to do, because the value of parameter n is in register A already at this point. So I'm just going to comment here and say, assume register A already has n. If we get here from the conditional, it's not exactly a conditional statement, but we get here from the branch, from the JCI branch. There we go. All right. So now we get back here, and now we have to handle the recursive case. So the recursive case needs to call fib. It needs to call it once with n minus 1 as the argument, and then it needs to call it again with n minus 2 as the argument. And then we look at the return value of both of those invocations and add them together, and that becomes the actual return value of this of fib for this particular invocation. So, well, first thing first, let's call fib again with n minus 1 in it. So at this point, if you want to reload the value of n into register A, that's fine. Okay, it's not a problem. But we know that that value is in it already. So we'll go ahead and just make use of the fact, and then we say decrement A. So after decrement A, we will have n minus 1, the value of n minus 1 in register A. Now we are not changing the argument or the parameter that is sitting on the stack. We are only doing the calculations inside a register. So at that point, we can now push it on the stack. So we decrement the stack pointer and then store register A to where the stack pointer is now pointing to. So that pushes the argument on the stack, which is n minus 1. And then we also have to remember to push the return address on the stack. So by now, I'm hoping most of you, recognize this particular pattern. We load A with .6 plus, and then we decrement D, store to D where D is pointing to whatever is in register A, which is our return address, and then we can do a JMPI to the subroutine that we are calling. In this case, you might say, but this is tricky because we're calling fib from inside fib. Well, the design of the algorithm can be tricky. So in other words, writing a recursive subroutine can be tricky. But if the recursive subroutine is already given to you, the implementation should not be tricky. In other words, calling a subroutine, whether from itself or otherwise, makes no difference. Okay, so we are calling exactly using the same way. And after it is done, we have to increment D just once because we have the argument still sitting on the stack. So at this point, register A contains the result of calling fib with n-1 as argument. So we have to stash it somewhere. This is why I gave you the sample program with Johnny and Ryan. Okay, because that one also has two function calls, and we want to add the values of the function calls. So we're going to deploy exactly the same trick, right? So we'll push register A on the stack. In other words, we are saving the return value of the fib of n-1 on the stack so that we can retrieve and use it later. So to do that, we decrement D, and we store to where register D is pointing to, register A. So we are, in essence, saving the return value of the first call to fib on the stack. Okay, we got a question in the text channel. What does decrement D after the .6 plus mean? It means we are decreasing register D by 1, and register D is our stack pointer. All right. So now that we have saved fib of n-1 on the stack, we can move on and call fib again, but this time with n-2 as our argument. Okay, we got two people typing, so I'm going to wait a little bit. Okay. Okay, so the .6 plus has been explained quite a few times. So I'm not really sure. And we explain why it is .6 plus. Okay, so I will explain it one more time. And this may be the third or fourth time that I'm explaining this, which means you might want to go back to earlier recordings of earlier lectures, because I can only give you a quick explanation, otherwise I won't have enough time. So dot means the address of the instruction okay, so let me turn on the line numbers. That makes it easier to explain. So when we look at line 17, that dot is representing the address of the LDI instruction. So .6 plus is the address of the LDI instruction plus 6. And that turns out to be where we want the subroutine to return to, because 0, 1 is the LDI, 2 is decrement, 3 is the ST instruction, 4, 5 are the JMPI fib instruction. So 6 would now be the increment D instruction, which is where we want the subroutine to return to. That is why we use .6 plus on line 17. All right. Alright, so now that we have saved the return value of the fib of n-1, it is time to push n-2 on the stack and then call fib again. We kind of have to reload n from the parameter itself. So you might think, oh, okay, it's kind of the same thing. LDIA with n, and then add AD like this. But this time we actually need load A with n1 plus, because there's one more item on the stack at this point. Okay, so we got a question in the text channel of why we're incrementing and then decrementing. So it is correct. Okay, so you're correct that I could have commented out both, and the program will still work exactly the same way. But the reason why I have both of these here is because the increment D is for one purpose, and then the decrement D is for a different purpose, which I have just mentioned. So if the question of why do I do that, the answer is I want to make it clear that you have to deallocate the argument, and then the decrement belongs to the pushing of the return value of the first call to fib. So they semantically speaking, they belong to different portions of the code, but functionally speaking, okay, they cancel out each other. So it is as if we do not have either in the instructions. All right. So now we have the address of n in register A again. So you really want to know why we have the 1 plus here, okay? And I'm not going to explain it one more time because I think it is best for you to think about this and look at the trace to find out why we need to do this, okay? Because it has to do with we got one more item on the stack. So the offset from where the stack pointer points to parameter n is now one more than what the label is defined to, okay? So now that we got the address, we can load AA again. So we get to the actual value of n. And this time we have to decrement it twice because we are trying to get to n minus 2. So at this point, A has n minus 2 in it, and it's time to push it on the stack. So we got decrement D, STDA, sorry, to push it on the stack. And now we are ready to call fib again. So to call fib again, it's really the same thing as from line 17 to line 21. So I'm just going to copy that. Okay, so line 17 to line 21, copy to here. There we go. And of course, it is a good idea to double check to make sure things make sense. Okay, so I'm just gonna double check here. So register A now contains, on line 31, register A contains the return address, and line 32, line 33 combined is pushing register A on the stack, which in effect is pushing the return address on the stack. Line 34 continues execution at the subroutine that we're calling, which turns out to be the same subroutine that we're in. Okay, but that really should not bother you because there's no problem doing this. Okay, and then line 35 is to deallocate the byte being used by the argument, because when the subroutine is done, why do we need to keep the argument on the stack? We don't. Okay, so that's why we are deallocating it. So at this point, we have the return value of fib of n minus 2 in register A, because that is the agreement between the caller and the callee. But we also have the return value of the fib of n minus 1 on the stack, because that's where we stashed it earlier. So now we need to retrieve the saved value, and we put it into a different register. So I'm going to put it into register B, and then I increment register D because I have just used up that item, so I need to deallocate that from the stack. So at this point we have the return value of the fib of n minus 1 in register B, and then we have the return value of fib of n minus 2 in register A. So it's just a matter of just adding those two. Now once again, the order is kind of important because I'm adding B to A because register A is the agreed upon register for returning a value. So it's handy to do it this way, because if I did it the other way, I'm going to have to copy register B to register A anyway. So by doing this, I'm saving that one extra step that I need to do. So now that we got everything done, we fall through to this point, which is basically just ready to return. So to return is LDBD. Okay, this is the return address. Once we consume it, we are going to increment the stack pointer to deallocate the return address from the stack. Once again, this is the agreement between the caller and the callee. The callee is responsible to deallocate the return address, and then we have a JMPB to continue execution in the caller. Now, which caller are we talking about? It could be main, could be some other subroutine, could be fib itself, but it doesn't really matter, because the way that we should think about a this particular recursive subroutine is really just to say that I don't really care who called me. Okay, it could be a recursive call, it could be from main, but the way that the caller and the callee agree on how to use the stack, how to use register A, and so on should remain exactly the same. So it really doesn't matter where we're returning to. We're just returning to whoever called me or whomever called me to use the right grammar. All right. So when this is all done, we're going to go back to line 1 and to put a note up here, because that's what we need to do to use the command line logisim to collect the trace eventually. And then I can just have halt here. I'm not even bothering to make a quote-unquote main subroutine, and I can just call it. Now, I'm pretty sure I talked about how to test this program, and I believe I talked about that on Tuesday and also on last Thursday. So obviously I bypassed a lot of steps, okay, because I recommended a lot of intermediate steps to write these programs to make the debugging easier. But I'm kind of bypassing all of those steps. But when you're testing it, it is good to test it with a small value first, and then gradually change that to a higher value. Okay. Now, if you're ambitious, you can always try it with a higher value. Okay, hoping that it works. But if it doesn't work, okay, you might want to go back and use 0, and test fib of 0, it should be 0, and then fib of 1 should be 1. Those are the two non-recursive calls of fib. Okay, once we get to 2, then it becomes recursive, which means if 0 and 1 works, that means the conditional statement is probably working. There's no guarantee. And then if 2 is not working, then that the recursive portion is not working, okay? Or or the conditional statement is not working either, okay? So you can test it in many different ways. So I'm just going to test it with 5, okay? So LDA 5, decrement D, STDA. So I'm pushing 5 on the stack. LDIA dot 6 plus. Decrement D again, STDA to push the return address, and then JMPI to fib, which is continuing execution at the subroutine. And when it gets back, I need to increment D to get rid of the argument sitting on the stack, and now I can halt. In other words, I do not have any local variable in main to store the return value of the fib of 5, but I can still test the program because the return value is supposed to be in register A by the time I get to line 10, so I can still see the value of this. I can still see the return value. So this is something that we can do with an assembly language program when we have a trace analyzer, so that we can actually see the value of registers. But if you're doing this in C or C++, then the return value cannot be seen unless you store it somewhere or unless you use it for printing purposes. So the way we debug programs in this case is a little bit different compared to how you debug a C program. Alright, so I think we are ready to give it a spin. Okay, so let's give it a try. And I am actually hoping that the program doesn't work, so I can illustrate how to debug a program like this. Alright, so let's cross our fingers and hope the program doesn't work. Yeah, I know. How often do you see people hoping that their program do not work, right? So we'll paste here, and the assembler is checking out things, and No, this is not my program. Or is it? Oh, I forgot to define the label. Maybe. Okay. I'm just reading the text channel. All right. So I got a basically an assemble time error of the JCI instruction because I did not define fib underscore return n, or I defined it using a different name. Okay, so let's go ahead and fix that first. All right. Oh, right. Okay, forgot. I did not give it a prefix. Sorry?
You're watching Rebecca's painting thing?
I'm watching class.
Oh.
Alright, so let's do this one more time. And paste it here. Alright. I mean, there's just one line of change, but I could have just, changed it in the spreadsheet. Okay, so this time we do not have any errors. Okay, very good. Then we get to RAM file and download this as a CSV file. There we go. And we'll save it as fib.csv. And then we switch to the command line and retrieve the previous Java command. So yes, I still have not written my script to do this automatically, but it's pretty easy. Alright, so we paste it here and just replace all the swap with fib. There we go. Press the enter key, and this time it takes a little bit longer. Okay, not a whole lot longer, but it takes a little bit longer because the amount of execution time is exponential compared to the parameter passed to fib. So that's why I was expecting it to get a little bit longer, but not by much. So now we get to the trace analyzer, and then we import. And we use fib.tsv. Now you don't have to name the files as as tsv because any file name is fine, but I use it because it is really a tab separated value file, and this is an appropriate file extension to use. Okay, just double checking. Replace current sheet tab and no. Okay, that should be good. Alright, so now we get to summary first. Yeah, we kind of have to wait until the progress bar is all done, but then we know where the last row is located, which is row 1602, 1602. So we use edit. Okay, I'm just looking for a quick way to get to the column, the row that we want to get to, and I do not know of a shortcut to do it. If someone knows how to get to the last row, or if you know the row number, that would be handy to do. But it's not too bad to do it this way either. Just keep scrolling down until we get to the end. There we go. So the first thing I want to check is whether the stack is balanced or not, and it is indeed balanced. Okay, so this is good. This is a good sign that we have used the stack correctly. Everything is balanced. And then I'm looking for the last update to register A, because that would be the return value of calling fib with an argument of 5. So that would be 5 here. So I'm pretty sure that is not correct. Okay, the fib of 5 is not 5. And to get to the sequence of Fibonacci numbers, or this sequence, we can just do a quick Google search, and the first one is probably Wikipedia. Nope, second one is Wikipedia. That's fine. Oh, actually, it is 5. I picked a wrong value to test. because the fib of 5 is actually 5. Let me see the sequence here. Okay, so this one is not. Okay, this is the one that we are using. So fib of 0, fib of 1, fib of 2, fib of 3, fib of 4, and fib of 5 is 5. All right. So I cannot really tell whether the program is working or not, because if I have the wrong condition and it just returns n, well, I would not be able to differentiate. Well, actually I can, because if that is the case, we wouldn't have 1600 lines of trace. So I'm fairly sure that the program is working at this point. Alright, so I'm going to open up the floor and see if there are any questions about this program. Alright, I'm not seeing anything in the Discord text channel, so I'm guessing some of you are thinking about it, processing. Alright, so what I'll do is I'm going to zip this up so that you can have a copy of this. Just for your reference. You can use it in the final exam if you find that this is useful. That's fine with me. So let me create fib.zip. We'll put the C, the TTP ASM, the CSV, and also the TSV file. Those two really should not be needed, because you can use the assembler to get back to the CSV, and then once you run the program, you can get back to the TSV. So they really are not needed, but I'm gonna pack everything in anyway. So we'll go ahead and upload fib.zip to the text channel, and this is the solution to the last lab, and have it uploaded, and there you have it. Okay, so you can do whatever you want with the zip file. My recommendation is to go in and comment it. Okay, I intentionally did not comment while I was working on the source code. So when we look at the actual code of fib, you can see that I have very little commenting on it, because I want you to do it. Okay, I did talk about, as I wrote this program, I was talking to myself, and I was definitely explaining what each instruction is for. But unless you have a very good memory, you probably have forgotten what I said. So it is a good idea for you to get through this program and comment on each line of why that line exists. Okay, what is it doing in this program? What is the significance of that line? So I think that would be a good thing for you to do. Look at this as one way to prepare for the final exam. It really is. I mean, this really is a good way to quote-unquote study for this class. But that is assuming that you already understand all the opcodes, what they do, and so on and so forth. So even though the final exam is not intentionally comprehensive, you still need to understand a lot of the concepts that we have talked about in the past, including signed versus unsigned, the flags, the significance of the flags, and so on and so forth. Okay, so all of that stuff is still important, even though I may not have specific questions asking about those topics. Alright, so we got one text entry in Discord. That is our assignment, or is this a practice? Well, it's sort of both. Okay, because I'm giving you the solution of the lab, which is kind of your assignment. I'm not sure what Tom is referring to. Is Tom referring to the program that I just did, or the commenting of the program? Oh, okay. Yeah, that's just the solution. I mean, some of you got it done, okay, and then you can just compare my solution with your solution, okay. If you somehow did not have enough time to finish the homework assignment, it's not a super big deal, because all the labs add up to 20% of your grade. So it's not going to be a whole lot if you're just looking at 1 or 2 or even 3 of the homework assignments. But it is what you have learned in the homework assignment that is important. Okay, so so I don't know what you want to do with the zip file. I mean, some people can choose to completely ignore that, and that's fine too. Okay, I'm just giving you that file so that you can decide what you want to do with it. All right. So, are there any questions? All right. Looks like we do not have any questions about Fib. So what I'll do next is I'm going to show you the final exam of the summer session of this class. I taught this class in the summer as a kind of compressed class because the number of weeks in the summer session is exactly 1/2 of 16 weeks. So I only got 8 weeks to teach this class in the summer. And so what I'm going to show you next is the final exam for the summer, which is, well, it is what it is. Okay, it's not going to be the same as what you're going to get, maybe not even in the format, but I'm going to show you what it is. So fx.c is the C code. fx.ttpasm is the faulty implementation of the C code, and it is not here because I forgot to unzip it first. Okay, there we go, unzip. Alright, so there are 3 questions in, no, that cannot be right. Okay, it's just fx.c and the text file. There we go. And I'm going to copy the text file into a ttpasm file so that we can have syntax highlighting. There we go. So now we can look at the C code. Okay, side by side. We want it side by side. fx.c and then fx.ttpasm. There we go. Much better. Okay. So in the final exam of the summer session, I basically gave my students the C code, okay, which people can totally compile. Okay, you'll use the debugger, use GDB or use online GDB to examine how that program works, and so on and so forth. And I'm also providing a faulty implementation of the C code on the assembly side, on the right hand side. And it's just a big huge debugging session. Okay, so the score of my students in the summer session is based on how many bugs they can catch out of the assembly implementation. So you're gonna have something like this. So the format is probably about the same. The program is not going to be the same. Alright, so we got the C implementation of F on the left hand side, and then we got the assembly implementation on the right hand side. So we're gonna go compare those two and see if we can find any bugs. Alright, so the first thing we need to do is to see whether P is, to check out what P is pointing to, and if it is pointing to something that is non-null, meaning non-zero, then we have to do this. If on the other hand it is pointing to a 0, then we're going to return x, which is one of the 2 parameters. So the first thing we want to check would be the offset, or the labels indicating the offsets, and make sure those things are defined correctly. So we check it and we go like, okay, since we do not have any local variables, so this checks out okay, because the return address is the last thing pushed, and then the first parameter is the second to the last thing pushed. The first thing that is pushed is P, so the offset seems to check out. Alright, so then what we need to do is to see, okay, how do we get to P? Okay, in other words, we want to see whether P is pointing to a null value or not. So we look at LDICP, add CD, so C has the address of P at this point, LDCC, so we are getting P, and then LDBC, which is loading what P is pointing to, what the parameter is pointing to, and then we have an AND BB to check out whether B is 0 or not. So I don't need to compare to 0. Okay, 0 is kind of special to see whether a register is 0 or non-zero, and can get the job done. And then we have a JZI to else, okay, because if whatever P is pointing to is null, we want to get to the else case, okay. And then we continue on with the increment instruction, increment C. The reason why we have an increment C is because we need to get to P plus 1. Okay, now this is P plus 1 in the C code and not asterisk P plus 1. So that's why, increment C is correct, because register C still has parameter P in it. Register B, on the other hand, has what parameter P is pointing to. Okay, so they're different. And then we have a decrement and a store, so we're pushing P plus 1 on the stack first. So that is also correct, because this is the last argument, and then we want to push this messy thing on the stack too. So now we have to look at that messy thing and determine what we need to do with it. So we load C with 48, which is probably this 48 here, and then we subtract C from B, which is okay because we know register B has the content in memory that is pointed to by P. So that accomplishes this particular sub-expression, up to here. And then over here we are loading C with x1 plus. The 1 plus is necessary. The 1 plus is necessary because at this point P plus 1 is already pushed on the stack. So all the labels indicating all the offsets, indicated by the labels, they are now all off by 1 because we got one extra thing on the stack. So that's why LDIC x1 plus is loading the correct offset relative to where the stack pointer is pointing to at this point. And then we add CD, which means C now contains the address of X. And then we have a LDCC, which means C is now the value of X. So what comes next is looks a little bit confusing, because I want to calculate X times 2 and then X times 8, and then we add those two. Then someone is going to say, but Tech, your toy processor cannot do multiplication. That is true, but multiplication is not really needed when you multiply X with a power of 2. So CPR-AC is really just saving X to another register, which is register A, and then I proceed to add C to C 3 times. Okay, so the first time I double, I get 2X. The second time I double, I get 4X, and then the third time I double, I get 8X. So at this point, register C has 8 times X in it. And then and then A at this point is what C used to be, which is the value of X. So I just have to add A to A. So A is 2X, and then we add B to C. So register B contains asterisk P minus 48, and then we add A to C, and register A has 2X, and then we decrement the stack pointer and then push register C on the stack. And Aiden is giving me, no, it is not good. Because you are, no, that's not 10 times C. That becomes C times 2 to the power of 10, which means it's going to be 0, because you'll be shifting zeros from the right hand side and shifting other bits through the left hand side, and the byte is only 8 bits wide, so if you shift 10 times, you won't have anything left. Yes, copy first, and you can potentially do it that way. Yep. Alright, cool. And I'm kind of surprised that I haven't found a single bug yet. So maybe this is the one that has no bug in it. Well, maybe. We'll see. Okay, so we decrement D, we push C on the stack, and that would be this big huge mess. Okay, this big huge mess is in register C at this point, and then we push the return address on the stack, and then we call F recursively because that's what the then case of the ternary expression is supposed to do, is to call F recursively. And when we're done, we come back and we increment D twice because we need to undo the 2 arguments that were pushed on the stack. And then we get to F return because we are done with the then case at that point. So I'm reading the text channel here. There's no way to do C equals to 10 times C by not writing each one. Well, we don't have a multiplication instruction, so there's no easy way to do it. You can do it I mean, Aiden's way is going to work if it is all, add AC, add AC, add AC, and then you have to zero out A first. That will work. So by the end of 10 add AC, you would have 10 times C stored in register A. Or you can do it my way, which is a little bit more efficient because I'm only relying on left shift operations to get to the value that we want to get to. But there's no easy way to multiply a register by any constant. Alright, so the else case is corresponding to just getting the value of x as our return value. And at that point, oh, okay, this one looks suspicious here, okay, because we really should not have this 1 plus here, because when we get to F else, okay, we should not have pushed anything on the stack. So this 1 plus here is suspect, okay. So I will just write down here, okay, the 1 plus may not be needed here. But I'm going to double check first. So I'm going to go all the way back and get back to the JZI to F else, and we can see that we haven't really pushed anything on the stack at that point. So that means, I would probably be correct here. So I'm going to comment out the original code, paste it, and change it in the pasted version. Okay, so this way there's a way for me to revert back to the original code if I ever needed to. Okay, and then we get to return. It is going to retrieve the return address, deallocate it from the stack, and then continue to whoever is calling me. So that seems okay. All right. And Aiden is correct. I could remove 1 line if I shift 1 first because the 2 is common between the 8 and the 2. It's the largest common factor. There we go. LCF. Alright, so now we look at G. Okay. Alright, so G is a little bit more complicated. It is also recursive. So we'll go ahead and check it out first. Okay, so once again, we check it out by looking at the offset first. It does not have any local variables, so the return address is indeed what the stack pointer should be pointing to. And then P is the first one. I changed it because P was used in the first subroutine already, so I had to change parameter P to Q. So when you see Q in the assembly code, it really is corresponding to P in the C code, so it looks a little bit confusing that way. So Q is the return address 1 plus, that's good, and then V is Q plus 1, that is good too, and then M is the last parameter, so it is V 1 plus. So everything checks out over there. Okay, we got some comments in the text channel. So when we change the errors to on the exam, do we need to just change it and explain? Yes. So there's a specific format for this particular version of the test. So when you remove a line, you have to comment out the line, and then you have to use a keyword to say that this line is removed. If you change a line, then you have to kind of comment and specify which part was changed. And if you are adding a new line, you use a comment to basically say this line is inserted into the original code. So there's a very specific format that I was expecting. But that is kind of more clerical than anything else. So I would much rather spend the time to talk about the program instead of the formatting. But that is a good question. All right. So getting back to the program. So we have LDIBM and then add BD. So by this time B becomes the address of M, and then by this time it becomes the actual value of M, and then we have AND BB. But Tech, you just said that AND can only be used to see if something is 0 or not. This is not 0 or not. Well, AND would also check whether the sign bit is set or not, because the sign bit and also the 0 bit or the flags, they are affected by every single operation through the ALU except for increment and decrement. So, but what I do next is wrong. Okay, this is not JCI. This should be JSI. Okay, so I'm gonna have to indicate here, changed from JCI to JSI, because the sign bit is bit 7, and doing the AND operation would also affect the sign flag. It will reflect the result. It will reflect the state of the sign flag after the AND operation. But AND BB doesn't really do anything to register B. It just basically pushes register B through the ALU just so that I can change the flags. Okay. And now we have JSI to then. So let's check whether that is correct or not. Okay, so so people who are not using the voice channel might want to turn off your mic in Discord, because I can hear background sound from Alex. Thank you. And then we have Daniel typing. Okay, so I'm gonna let Daniel finish his typing first. Okay. Could I convert the 80 to decimal and use that instead? You could, but 80 in hexadecimal is 128. So you could compare it to 128. So one of the things about this exam is I do not want people to make unnecessary changes. In other words, if somebody does not understand my code and decides, you know what, I'm just going to change this entire program to my implementation, that probably would not get any points. So I do only want people to make changes when there is a bug. Okay, so Daniel says, I'm not sure how I check it. No. There's no comparison, Aiden. So Aiden says, whether it's great. Yeah, we are only checking whether it is 80 or not, which is what the C code is trying to do. Oh, right. Okay, I see what Aiden is saying. What if M is not exactly 80, but has that particular bit turned on? Okay, so that is correct. Okay, so the program does not, the assembly code doesn't do what the C code is asking it to do. So yes, so in that sense, we should change it. Yep, it doesn't check equality. That is correct. So, all right, fine, we'll do it the hard way, like really the hard way. All right, so we'll go ahead and change it so that we have LDI A with 128, and then we have a compare. And this time, with compare, and we're looking for equality, it doesn't matter which way we're comparing. So we can just compare A, B in this case. And if they are the same, which is JZI, then we branch. There we go. Yep. So that's exactly what we're doing, is to compare, which is a subtraction. And then we have a JZI. When they are the same, then we go to the then branch. So is that better, Daniel? Okay, cool. Alright, so if I do not go to G underscore then, that means I'm going to the else case, because it means M does not equal to 80 in hexadecimal. So in that case, I need to do a recursive call to G, and the last parameter is I need to calculate M plus M. Okay, but I'm relying on the fact that register B still contains M, so I'm just adding BB, which means we now register B has 2 times B, and then I push it on the stack. Then I need to push V on the stack, but since I already have M plus M pushed on the stack, so the offset to all the items are off by 1 now, and that's why I need the 1 plus in order to get to the offset to V. And then I add AD to get to the actual address of V, load AA to get to the value of V, and then we push that on the stack. So that looks good. And now we have to get to P. So this one now needs to be a 2 plus, okay? Add 2 plus to the expression, because we have 2 extra items sitting on the stack now. One of them is M plus 1 that we push on the stack. The other one is V, which we also pushed on the stack. So everything is now 2 bytes off compared to the labels. So once we have done that, then we can now compute the address of Q on the stack, which is P in the C code. And yep, so that's the address. This is the value of P on the stack, and then we push it on the stack. That's our last parameter. And then we have this code here to call G again. So you might have noticed that instead of an LDIA and then a .6 plus, I have a .5 plus. And that's perfectly okay, because I put the decrement D in front before the LDI instruction instead of after the LDI instruction. So the offset between this particular LDI instruction and where the subroutine needs to return to is indeed 5 this time and not 6. Okay, so I load the return address in register A, push it on the stack, and then continue execution in the called subroutine, which is G. So that's everything is good so far. Increment D twice. That would not be good, because there are 3 arguments on the stack. So I need to remember to add 1 more increment D. Okay, so add this because we have 3 arguments on the stack, or the arguments take up 3 bytes instead of 2 bytes. And then the next thing we need to do is to have P equals P plus 1. So this time we have LDBQ, which is the offset, add BD, which is the address. That would not be good, okay? We're not ready to do increment A and then store A back to B. Certain things are missing, okay? A few things are missing, because we never really got to the value of P. We only got to the address of P. So what is missing here is an LD instruction, LDAB. So now register A is the value of P. We add 1 to it, so that register A is P plus 1, and then we store register A, which is P plus 1, back to where B is pointing to. But B is the address of P. So we are updating P with P plus 1 with that store instruction. And then we have a JMPI to G underscore continuation, which is right here. Okay, so G underscore then has nothing to do, which is perfectly okay, because the then statement, there's really nothing to do here. So we are good over there. And then we get to this part which is trying to implement this instruction here. So we'll go through all of these step by step. I'm just looking at the time. We got 20 minutes left. So LDIAV is the offset to V. Add AD would get us to the address of V. LDAA would get to the value of V. And then we do the same thing with M. So by this time we have register A has V, register C has M, and then we perform an AND operation because there's a there's a bitwise AND over here, and we perform the bitwise AND over here using the AND instruction. And if it is 0, we go to the ternary else, which is the 48. If not, we specify a value of 49. Okay, so that looks correct, but there's something missing here, because at the end of the then case, I need to jump around the entire else case. So I already have a label called g_ter end. So I need to jump around the else case to get here, because otherwise it makes no sense to load A with 49, because right after that it's going to load A with 48. So that's why we need to have this extra instruction here to jump around. Okay, added to jump around the else case. There we go. Okay. So now we get to almost the last statement. This is the second to the last statement. So okay, so this is the offset to P. This is the address of P, and this is P itself. Okay, and we have a problem because this is the left hand side. Okay, oh, I take it back. We computed this entire expression on the right hand side, but we haven't done a single thing about it. So we have to store that to where P is pointing to. So let me do it one more time. So we have the offset to P, we have the address of P, we have P itself, and then we don't need the extra one here. So this one of them has to go. Okay, this is all right. So we basically, you like the first final exam more? All right. So register C has P in it. So now we're going to store A, which is the entire right hand side, to what P is pointing to. So that is correct. Okay. And now we increment C so that C has P plus 1 in it. And then we subtract AA, which turns A to 0. And then we store A to where C is pointing to, which is P plus 1, and that is correct. And then we have decrement C, copy C to A. So we are moving down to here. We're trying to return P, back to the caller. C is now P plus 1, so decrement C will get C back to P. But we have to copy that to register A, because register A is the agreed upon register to specify a return value. And then we get down to here. We retrieve the return address into register C. We deallocate that byte that was used on the stack, and then we continue execution in the subroutine. And then we get to main. So main also needs debugging potentially. So we'll go ahead and look at the C code first and find out whether it is done correctly or not. Alright, so we have buff length defined to be 9 in the C code right here, and in assembly we just make a label and define it to be 9. So main is going to have, it needs some space for the local variable buffer, but since it is the only local variable, so after we do the allocation, that is the offset of 0 from where the stack pointer points to is exactly where we can find the local variable buffer. So the offset of 0 is correct. Main underscore local underscore var underscore size, which is how many bytes are used by the local variables of main. It is buffer, which is the offset, buff length plus So that is correct, okay, because that tells us how many bytes are being used on the stack for local variables in main. So we load that constant into A, we subtract that much from the stack pointer. That's how we allocate. And so my way of doing things is to make sure that I deallocate it to, at the very end of main. So we see that is done with these two instructions, so that's good. And then we call G the first time using the result of F here. So let's check whether that is done or not. Alright, so the 1, which is the last argument, is pushed here. We load A with 1, decrement the stack pointer, and then store to where the stack pointer points to. That's pushing just 1 on the stack. And then we have to call F with 87 as a string and a 0, as the first argument. Okay, so this is where things get a little bit kind of tricky, because to pass a string, we have to define the string somewhere else, because a string is technically the address of the first byte of the string. So that is defined all the way down here. Okay, this is how we define the literal string. Is really just to give it a label, and then we define the bytes one by one. 48 is the ASCII code of 0. So when you add 8 to the ASCII code of 0, you get the ASCII code of 8, and the same thing with the 7. And we always need a null terminator, because all C strings are terminated by a null. So that's why we have a byte 0 here. But the label const string A is really the same thing as the string in double quotes in C code. It is the address of the first byte of a string. Okay, so getting back to here, that's the first thing we push on the stack, which is correct because it is the last argument. So we push that on the stack. And then here we push the 0 on the stack, which is also correct. And then we push the return address on the stack, and that's done by a decrement D first, and that's why it's a .5 plus instead of a .6 plus, because the decrement D is no longer between the LDI instruction and where the subroutine is supposed to return to, which is this point here. So when that subroutine call, when F returns on this line, it gets back to here. We have to increment D to undo the space used by the 0 and the string, 87 on the stack. And then we continue to push the return value of F on the stack, because the return value of F in return becomes the second argument to call G. So that's why we have to push that return value on the stack. And now the last thing we need to do is to push buffer on the stack. When you push an array, quote unquote, an array on the stack, you're always pushing the address on the stack, because there's no way to pass an array by value in C, nor C++. So when you're passing an array as an argument, you're only passing it using the address. But the problem is we need a 2 plus here, because we have 2 extra things sitting on the stack at this point. The first thing we pushed was the constant 1. The second thing that we pushed was the return value of calling F. So those 2 extra things are now sitting on the stack, which means the offset to items relative to where the stack pointer points to, everything, all the labels are now 2 bytes off from where they're supposed to be. And that's why we have the 2 plus. And then we add BD to get to the address of buffer. And that is what we want to push on the stack. But when you look at the code, we have the decrement, which is good because we want to reserve the space first before we store. But the ST instruction is missing. So we need a ST instruction here. So we have STDB. There we go. So we are storing, we're pushing the address of the array on the stack. And then we push the return address on the stack. And then we perform the continuation. We perform the jump to subroutine G. When we get back, we increment D 3 times to undo the arguments that we just pushed on the stack. And that should conclude the main subroutine. Phew, that is it. All done. Cool. Not cool. And we have 10 minutes left. Very good question. I like that question. So the question is, what does this program do? Well, let's take a look at the C code. Okay, so this part is not assembly language programming. Instead, it is just trying to understand what the C program is trying to do. All right. So let's look at F first. It actually has comments. Okay, F interprets the string pointed to by P and returns the value of the string. Parameter X must be 0 from the top level caller. In other words, what F is doing is it looks at, okay, so it makes an assumption first, okay? The assumption is P is a string that has a base 10 number in it, okay? And we are talking about unsigned, okay? So we are talking about, a string of like 18, 28, 05, or just 5, or something like that, okay? And all it does is to say, okay, if you give me a string that has 5, 8, and then a null terminator, and X is a 0 to begin with, it will return the value of 58. Okay. In other words, it is a very strange version of string to ATOI. Okay, ASCII to I, ASCII to integer, and it's recursive, but that's what it does. And what G does is to reverse it. Okay, so G converts the numerical value V to an 8-character string of zeros and ones. So it's not quite exactly the opposite. It is converting the numerical value of V into a string that only consists of zeros and ones. In other words, it will give you a printable version of the binary representation of a value. So that's what G does. So when we have this program, okay, so we first convert 87, we interpret 87 as a base 10 number, and that's what F is going to return, which is the value of 87. And then what G is going to do is to take that 87, which is a value, not a string anymore, and convert it into a base 2 representation. And that representation is going to be stored in buffer. So when G is done, the buffer excuse me, will have the binary representation of 87, which is 0, 1. Okay, my base conversion is not that fast. I need a piece of paper to help myself. So we have no 128. We have a 64, and once we have the 64, we have a 16 that takes care of 80, and then we have no 8, but we do have a 4, a 2, and a 1. So after the conversion, we would have let me double check here, and I think it only gets you, just trying to read it here, it's an 8-character string, and that's why we need a buffer to have 9 characters, because we also need 1 character for the null terminator. So we have 0, 128, 164, 0, 32, 116, no 8, 1, 4, 1, 2, and 1, 1. So we can expect to find 0, 1, 0, 1, 0, 1, 1, 1 in the buffer when this is all done. So does that explain what the program does? And it gets this done in a very kind of obscure way. That was kind of the point. All right. Well, we got 6 more minutes. Let's go ahead and check out the assembly code and see if it works. Okay. So we get out of the editor, and then we'll go ahead and see if the assembly code works or not. There we go. Oh, by the way, there's also a solution to this too. I can post the solution later. And then we get to the assembler, go to the source tab, delete everything in column A, paste all that, go to RAM file, and then download it. Alright, we'll call it fx.csv, and then switch to the command line interface, go back to the Java command line, and this is fx, and fx over here. Alright, program is done. We get to the trace analyzer, go to sheet 1, and we want to import fx.tsv. The tab separated file is the log, and then replace tab no. Import data. And then we get to the summary to see how long the trace is. So this one is rather long. Okay, so now the question is, how do I know the program works or not? So if I just really want to check to make sure that the program at least seems to work, the first thing to check is whether the stack pointer is balanced or not. Does register D get back to 0 at the very end of this program? So we have to get to row 2576. Okay. Alright, so we get to 25. Okay, there we go. So the stack pointer did get back to 0, which is good. Okay, so that means the program didn't crash, the recursion did not become endless, and so on. And now we need to check the string to see whether, I mean, there are a few ways to do this. Okay, you can first check whether f returns the correct value or not. Okay, let's do that first. So what I mean, okay, let me go back to the C code first. So let me go back to the editor. So the first thing we need to check is to see whether the return value of f is correct or not. Okay, because if that is wrong, then there's no way G can get the job done correctly. So then we have to do that. We have to use the assembly instructions to find out where in main we call f and have the return value of f being pushed on the stack. So we get down to, let's see, where are we calling JMPI to f is where we called it. Alright, so right here, okay, at this increment D instruction, register A should contain the return value of f, which should be 87, but in hexadecimal, because the trace analyzer only look at things from the hexadecimal perspective. So 87 in decimal is 57 in hexadecimal, because 87 is 5 times 16 plus 7. So 57 is what we're expecting at this instruction. So now we need to go to the assembler and go to the assemble tab to find out where that instruction is located. So it takes a little bit of kind of navigating, and this is why the more you have done this when you're doing the homework assignment, the faster you can get this done, in the exam. So we are looking at the execution of the opcode at location 8D. So when we get to the trace analyzer, we want to focus on just column A this time, and we want to find 8D in column A. So let's do that. Control F doesn't do what I really want to do. So I need to go to edit and then go to find and replace and specify 8D. And since I selected the entire column A, it by default would search within only that column. And this time I don't need to use regular expression because A to D is fine. Okay, it's not a pattern. Let's see. What did it do? It never got to 8D. This is the problem with having something that's recursive, because it's a long trace, and that's why we have to find definitive places. So we'll do it one more time. We're looking for 8D, and we are trying to find it in column A of analysis. Okay, find. There we go. Okay, I don't remember exactly. Oh, I just clicked done. Okay, duh. Okay, so here's 8D, and we want to find out what the value is in register A right before we get to this execution point. So that would be in column D. So we want to focus on column D and find out what is the value of register A. And here is our 5.7 in register A. So we now know that the function call to F in main returned the correct value. Okay, so knowing that, now we can look for the zeros and ones that we store into buffer. Okay, and buffer is going to be reflected in column C, because every time we write to the buffer, we are writing to RAM, and specifically we are looking for the last 9 locations in RAM. So we have FF, and then you just count backwards, right? So we got FF, FE, FD, FC, FB, FA, F9. Okay, let me do it faster, the smarter way. Okay, so we have 15, which is F, minus 9. Actually, it's just minus 8 because it's 0 oriented. So it's 7. So F7 is the lowest location where we stored something. Okay, so that makes it easier because now we can just look up column C, and then we search just using this column. And we want to look for F, and then the next character can be 7 to 9, and then A to F. Okay, so this is how we can specify a regular expression to do that. And we want to see a equal symbol after that, because we don't want to find cells where F7 all the way to FF appears as some part of it. We want this to be the first part of it. So this is the regular expression that we want to specify. So we say search using regular expression, and specific range is C, column C. That is fine. So now we click on find. Okay, so if you just kind of write it down, okay, this is the leftmost character because it's the first one. Is 0, 0, 1, 0, and then we have 0. Oh, okay, that's the null character. I miscounted. Okay, let me go back to the beginning again. I miscounted. Alright, let's do it one more time. Okay, find again. Okay, so okay, it's still not getting all the way back to the beginning. I'm not sure how I can change the search to all the way back to the beginning. Let's try that one more time. Nope. Okay, so finally we got back to F7 is a 0, F8 is a 1, F9, this is not F9, this is F8, is a 0. Okay, so the program did not work. It did not increment the pointer to get back to the to get to the next location. So the program did not work entirely. Yeah, I know F9 was there, but we should be seeing the progression of, F8, F9, and so on. So it did not work. Okay, the values are correct. So we have 0 and then 1, 1, 1. So it has all the correct content, but it did not get to the right place. Alright, so let's debug this. Now, if you want to sign off now, that's fine with me. But on the other hand, if you want to know, how to debug a program, well, this might be interesting. Okay. Alright. So this is G. Okay. So we know we have the correct V to begin with. Now, the other thing you can do is to really just take the C code and go to online GDB and run it in online GDB just so that we know the C code is correct, which I'm fairly sure about. Okay, so I'm pretty sure the C code is working correctly. So what I'm missing, I'm thinking, is this part here. Right after G is done with the recursive call, I am forgetting to increment P before we get to this point here. And that's why it is overwriting the same location over and over again. Alright, so if this is what I'm suspecting, how do we find that bug, right? So the first thing we need to do is to go back to the assembly code, and this time we are looking at function G, and we are looking at the code right after G calls itself recursively. So we have to look for the JMPI to G, and then we are undoing all the parameters. So this is where we are looking for, okay? And we want to look at these instructions where the cursor is, line by line, and make sure that we're not missing anything. So B has the offset, B now has the address, A has the value of P, okay, we add 1 to the value of P, and then we store that back to P. So that seemed correct to me. So with each recursive call, I think the C code itself, let me think about this. The recursion ends when M is 80. So that is defining the bit mask. So when we are dealing with the last bit, then it stops the recursion. Otherwise, M is a bit mask, so this is the same thing as a left shift, because M plus 1 is just 2 times M, which is the same as left shifting by 1. And it is calling it with just P, because we want the most significant bit to be stored as the first character. And then after that, it comes back, and then we add 1 to P, so that P points to the next location. And we're supposed to return P here, which is supposed to be after we have added 1 to P. Okay, so the problem of this code has got to be at this portion. So somehow I'm not adding 1 to P correctly. I skipped it. No, the values were calculated correctly. So we know this part is done correctly. It's just where it stores it is not right. Oh, you know what? I know exactly what is wrong with this code. Okay. I got it. Okay. So right here. So after the function returns, I'm supposed to store the return value to P. I didn't do that. Okay, there is no code here on the assembly side to do just that. Okay, so that's one thing that I need to do. Okay, so what we need to do is to do a store here. So we have the store to where B is pointing to, A. So this register A at this point is the return value of G. This B is calculated already to be the address of P. So we need to store that first. Now, if you want to combine these two statements and just say, well, in assembly code, it's pretty easy to do because we just have to increment A before we store. That's fine. Okay, we can say increment A before we do the store, and then we don't need the other instructions anymore. So that should fix the problem. All right. So let's check out whether this is fixing the problem or not. Okay. So once again, the problem was I did not store the return value of G back into P. I went through the whole motion to call G. G probably gets whatever it needs to done correctly, but I forgot to store the return value of G into P before I increment P by 1. Okay, so that is the step that is missing, and now it is done by incrementing A. So A is whatever the return value of G is plus 1, and then B is calculated to be the address of P already at this point. So storing A, which is the return value of G plus 1, to where P is, is what we want to do. So I'm combining these two lines of C code into this chunk of assembly code. So let's go ahead and give it a try. And we want to repeat the xclip command. Oh, okay, that won't work because I need the cat first. So we'll just go ahead and do this, cat, and then go back to the assembler, go to the source tab, get rid of column A, paste again. All right, and then we get to RAM file, download it. Now, in the final exam, I'm not really expecting people to find each and every single bug, but I will be counting, how many of the bugs were actually found, and that basically determines the score. All right, so we get back to here, but I should be able to get the whole thing working. That's the whole idea of doing this. Okay, so we run it again, and then go back to the trace analyzer, and get out of here, go back to sheet 1, import, the trace file. All right. So the number of rows should change a little bit, but not by much, because we changed the program a little bit, but the structure of the recursion didn't really change that much. So now the program has 2542 rows, and we go back to analysis, and we really want to go all the way back to the first row, and then we highlight column C, because column C only registers whatever we write to RAM, and then we go back and search for exactly the same thing as last time. So we go back to find and replace, and then we specify F, and then the first location is 7. So we use up 7 to 9, which is the range that we can specify using only digits, and then the A to F for the rest of the hexadecimal digits, and then the equal symbol so that we are only focusing on these as locations that we are overwriting in RAM, and they are regular expressions, so it automatically turns on case matching. Alright, so let's give it a try again. So we have a 0, 1, 0, 1, 0, 1, 1, 1. Woohoo! Okay, so the whole thing is working now. Yay. So now the next question is, what are we going to do in the final exam. Okay, because we know the final exam is going to be similar, okay, in terms of the format to this one. The length may not be the same. I may give you a shorter program to do to debug. The first thing you want to do is to understand the C code. Okay, that's really important. Okay, now whether you want to run the C code on its own in a debugger, okay, that's up to you. Okay, you have all the tools at your disposal. You have online GDB, you have code blocks if you want to. So you have all those tools, but you got to understand what the C code is doing first. Okay. Then when you look at the assembly code, you can do what I just did. Okay. Just go line by line and make sure that it makes sense. Okay. Now, if you have enough time, okay, you can go through all the code. You have identified, everything that you can identify and fix everything, using the method that I just used, statically going through everything. If you have time after that, then you probably want to run the code using LogicSim and compare the behavior of the code with the C code. So that means you need to know how to check whether you're pushing the right arguments on the stack or not, whether the return value of the invocation of the subroutines are right or not, whether you're storing the right values into RAM or not. Okay, which is all the things that I did today. And once you find out that the assembly code is not matching what the C code is doing, then you have to find out why it is doing that. Now that's going to be probably the most difficult part. The last bug that I caught was probably the most difficult one, because that part really depends on how well you understand the C code. So by observing the symptoms in the assembly code, can you figure out which part of the C code is not implemented correctly that will cause the symptom. Okay, so I'm done with the lecture. So are there any questions about the demonstration today? I'm not seeing any questions. All right. So I'm not going to remove any of the videos that we have recorded, throughout the lecture. So I suspect some of those can be useful for review purposes. And I'm going to re-upload. By the way, I'm going to re-upload now the completed program. So we'll go back and redo the zip command. Nope, that's not what I want to repeat. I want to repeat the zipping of the fx stuff. So let me do it one more time. There we go. And I'm going to post that in the text channel. So this way you have a copy of that too. There you go. All right. So the idea is, I'm giving you all of this material so that you don't have to retype everything from just the program. You have everything already typed up, and everything is fixed already too. Now, if you want to see the changes that I have made, then you can download from the first fx.zip that I uploaded in the text channel. That's before I made all the changes. And then you download the last one that I uploaded. That's with all the corrections. So the idea is to look at the diff, or the differences between the two. And there are special tools that can help you with that too. In Windows, it may be a little bit different, but in Linux, there are really a lot of tools that can do this. So let me show you one tool that I use that may be helpful. So on the side, I am looking at, so this is the original code before I fix anything. So I'm just going to copy and paste it into a different file. Okay, so I'll copy that into fx-original or orig, dot ttpasm. So now we have two files. One is the original, and one is the final version. If anyone knows how to use Vim, there's a diff mode in Vim, which is quite handy sometimes. So you can do nvim-d, if I remember correctly, for the diff mode. And then we can use fx.ttpsm, fx-original.ttpsm. And the way it does it is really quite interesting, because it would highlight what we have done with the code, but it only highlights the changes. In other words, it will spot that on line 47, the original code has LDI A and then x1 plus, and then the new code has it commented, and then the next line is inserted because basically we just removed the 1 plus. On line 66 and line 67, this is how we changed it. So we changed it from the AND BB instruction to the actual comparison of 128. On line 78, we add the 2 plus, which is right here, whereas the original code does not have the 2 plus. So this is a really useful tool, to compare two text files so that we can quickly and easily identify the changes between the two text files. Now, for those of you who know, these tools, you can use whatever you want. Okay, I'm pretty sure in Windows, there are visual tools that can do this as well. But this is really helpful. Okay, in terms of reviewing the final exam that I just went through, because it will help you focus on just the changes. And it is important for you to understand why I made each change, what was the original bug, and why the change, what the change is and why it is necessary. Alright, so I think I'm done in terms of giving you ideas of how to study for the final exam. It really boils down to a really good understanding of the material. And all of this stuff here is really just to kind of help you understand the material. Are there any questions before I end today's lecture? Alright, I'm not seeing anything. So I'm going to turn off the live stream. I'll pay attention to the Discord text messages. If anyone wants to message me about anything, I'll be more than happy to answer the questions.